Welcome to Two Projects. In this video, we are going to explain the project YOLOv5 based model integrating separable convolutions for detection of wheat head images. Introduction. The project centers on predicting wheat yield by developing a robust model for the accurate detection and counting of wheat heads in outdoor field images. This predictive capability is crucial for informed agricultural management decision making, aligning with broader objectives of enhancing food security and supporting macroeconomic policies related to rural land and food prices. Accurate wheat yield forecasting plays a pivotal role in ensuring food security and guiding government interventions. The project addresses the challenge of precise detection in outdoor images, a task complicated by factors like overlapping plants, image noise, and variations in wheat appearances. The significance lies in providing reliable references for farmers and aiding macroeconomic regulation. And the project aims to leverage advanced computer vision techniques, specifically the YOLOv5 based model integrating separable convolutions. This model is designed to address the complexities of wheat head detection, offering improved accuracy and speed in real world scenarios. The approach involves overcoming challenges such as image distortion, varied wheat appearances, and the need for models to generalize across diverse growing environments. And the primary beneficiaries include agricultural stakeholders, farmers, and policymakers. Accurate wheat yield predictions empower farmers to make informed decisions in the field, while policymakers gain valuable insights for macroeconomic regulations. The project's outcome, a robust wheat head detection model, contributes to the advancement of precision agriculture, promoting efficiency and sustainability in wheat production globally. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to enhance wheat head detection in outdoor field images using advanced computer vision algorithms. The focus is on achieving accurate and efficient identification, crucial for predicting wheat yield, supporting agricultural decisions, and contributing to food security. And the project aims to build and implement state of the art algorithms including YOLOv5, YOLOv5 with CBAM, that is Convolutional Block Attention Module, YOLOv3, YOLOv7, YOLOx, FASTA RCNN, and SSD. Each algorithm is tailored to address the challenges of wheat head detection, considering factors like overlapping plants, varying appearances, and diverse field conditions. And the project involves a comprehensive evaluation of algorithm performance, employing metrics such as mean average precision, and recall. By comparing the outcomes of different algorithms, the project aims to identify the most effective solution for accurate wheat head detection. The ultimate beneficiaries include farmers, policymakers, and the agricultural sector, benefiting from improved decision making, resource optimization, and enhanced food security. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front-end framework used is Flask, backend framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is importing required packages. So the initial step involves importing essential packages such as NumPy, Pandas, Matplotlib, sklearn, TensorFlow, and Keras. These form the foundational tools for data manipulation, visualization, and machine learning, creating a robust environment for subsequent tasks. The second step is exploring the dataset. So, the dataset exploration phase encompasses reading and plotting images to gain an understanding of the dataset. The third step is image processing. This step involves pre processing images, including converting them to blob objects, defining classes, declaring bounding boxes, and converting arrays to NumPy arrays. These processes prepare the images for subsequent stages in the computer vision pipeline. The next step is loading the pre trained model. Here, the pre trained model is loaded and its network layers are read. Output layers are extracted, setting the stage for utilizing the pre-trained model for object detection tasks. The next step is image processing again. So further image processing involves appending image annotation files, converting color spaces, creating masks, and resizing images. These steps ensure compatibility and optimization for the subsequent phases. The next step is data augmentation. In this step, data augmentation techniques such as randomizing, rotating, and transforming images are applied. These augmentations enhance the model's ability to generalize and improve its performance on diverse datasets. The next step is installing the packages required for YOLOv5 in Colab. Here, the necessary packages for implementing YOLOv5 in Google Colab are installed, ensuring a seamless integration of the YOLO model for subsequent data processing and training. The next step is processing the data based on YOLOv5 model. So the dataset is pre-processed in alignment with the YOLOv5 model requirements. This includes organizing and formatting the data to match the model's expectations, ensuring optimal training performance. The next step is training and building the model. In this step, multiple YOLO models, including YOLO V5, YOLO V5 CBAM, YOLO V3, YOLO V7, YOLO X, along with other established models like FASTA RCNN and SSD, are trained and built. This involves fine tuning the models on the specific dataset to improve object detection capabilities. And in the next step, as an extension, exploration of additional models such as YOLO V5 by 6 and V8 is conducted, aiming to enhance the robustness and accuracy of the final predictions beyond the initial set of models. And as an extension again, a front-end interface is constructed using the Flask framework, incorporating SQLite for user sign-up and sign-in functionalities. This user-friendly interface allows users to input images, triggering pre-processing and detection using the trained models. So after signing in, users input images through the front-end, initiating the model detection process. So the given inputs undergo pre-processing, and the pre-processed images are fed to trained models, and the model infers and detects objects, applying segmentation and bounding boxes to identify and distinguish each object within the input images. And the annotated images showcasing detected objects with bounding boxes are displayed through the front-end interface, providing users with a visual representation of the model's predictions. Now we'll understand about the algorithms used. So the first algorithm built is YOLO V5. So YOLO V5, that is You Only Look Once version 5, is a real-time object detection algorithm that divides images into a grid, predicting bounding boxes and class probabilities for each cell. Renowned for speed and accuracy, YOLO V5 is chosen for its efficiency in processing images and suitability for real-time applications in this project. The next algorithm built is YOLO V5 CBAM. So YOLO V5 CBAM incorporates convolutional block attention module, that is CBAM, into the YOLO V5 architecture. CBAM enhances feature representations by selectively focusing on important parts of an image, improving detection accuracy. This modification aims to boost the model's ability to discern weight heads effectively. The next one is YOLO V3. So YOLO V3, an earlier version of YOLO, introduces a three-stage detection process and a feature pyramid network. It efficiently handles varying object scales and complex scenes, making it a suitable choice for this project's diverse weight-head images, overcoming challenges like overlapping plans and varied appearances. The next algorithm built is YOLO V7. So it is an upgraded version in the YOLO lineup, combining the strengths of YOLO V4, scaled YOLO V4, and RYOLO. Its main feature, the extended efficient layer aggregation network, that is EELAN, boosts learning capabilities, and with compound model scaling, it adapts independently in width, depth, and resolution. YOLO V7 stands out for efficient real-time object detection, making it an ideal choice for the project, offering a harmonious blend of efficiency, adaptability, and accuracy. The next one is YOLO X. So YOLO X extends YOLO V4, introducing efficient anchor assignment and PANNet. Efficient anchor assignment enhances object localization during training, and PANet improves feature integration. YOLOx excels in accurate and efficient object detection, especially in crowded scenarios. The next algorithm built is FASTA RCNN. So FASTA RCNN, that is region-based convolutional neural network, is a two-stage object detection algorithm. Its region proposal network efficiently generates bounding box proposals, making it suitable for scenarios where precise localization of weight heads is crucial. It is chosen for its accuracy in bounding box prediction. And the last algorithm built is SSD, that is single shot multi-box detector. So SSD is a single shot object detection algorithm that generates multiple bounding box predictions per feature map cell, capturing objects at different scales. Its ability to handle scale variations and produce accurate detections aligns with the project's goal of identifying weight heads in diverse scenarios. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis, I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis, I have recall scores and on y-axis I have algorithm names. So recall assesses the model's ability to capture relevant instances calculated as the ratio of true positives to true positives and false negatives. So this is MAP scores comparison graph. In this graph on x-axis, I have MAP scores, that is mean average precision scores. And on y-axis, I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have required dataset images on which we will train the models. This is sample folder in which I have images on which we will make the predictions. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is Notebook Jupyter source file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. These are Python main code files. This is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password, and click on login button. So it has redirected us to the detection page. So here we have to upload an image and the application will detect the weight heads in the image. Click on choose file button. So from sample images folder, I'm selecting the first image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected all the weight heads and has drawn the bounding boxes around the detected weight images. And we can also see the weight label, and we can also see a probability score which tells us how confident the application is about the detection. Click on back. We'll try giving another image. Click on choose file button. So this time I'm giving this image and click on open. So the image is loaded. Now click on upload button. So we can see all the weight heads are being detected. We can see the bounding box drawn around the weight heads. We can see the weight label and we can also see a probability score. Click on back. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the weight heads are being detected. We can also see the bounding box, the label and the probability score. So similarly, we can upload any image and can get the detections of the weight heads. Click on choose file button, select the image, click on open and click on upload button. So we can see the weight heads have been detected. We can see the bounding boxes drawn around the weight heads. We can see the label and we can see the probability score telling us how confident the model is about the detection. Click on back and click on sign out. So the conclusion here is the project successfully addresses the challenging task of weight head detection in outdoor field images, contributing to enhanced accuracy in predicting wheat yield. Accurate yield forecasts play a pivotal role in supporting food security, providing valuable insights for agricultural product management and macroeconomic policies related to rural land and food prices. So the project introduces and refines multiple algorithms including YOLOv5 based model, integrating separable convolutions to overcome complexities such as overlapping plants, image noise and variations in wheat appearance, YOLOv5 CBAM, YOLOv3, YOLOv7, YOLOx, FASTA RCNN and SSD, employing advanced computer vision techniques. Rigorous evaluation and comparison of these algorithms demonstrate their effectiveness in addressing challenges of weight head detection, achieving a balance between accuracy and efficiency. Through an extension effort, the exploration of additional models like YOLO V5 by 6 and V8 significantly enhances the project's predictive capabilities. This expansion ensures a more robust and accurate final prediction for wheat yield, broadening the applicability of the model across diverse conditions. Going beyond algorithm development, the project integrates a user-friendly front-end using the Flask framework. This practical implementation facilitates user testing, enabling stakeholders to interact seamlessly with the model. The incorporation of user authentication with SQLite ensures secure sign-up and sign-in processes, elevating the overall user experience. So, the primary beneficiaries include agricultural stakeholders, farmers, and policymakers. The robust weight head detection model empowers farmers with informed decision making in the field, while policymakers gain insights for effective macroeconomic regulations, contributing to the advancement of precision agriculture globally.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.